Hey guys, Scott here. Today we're going to be looking at some integration by substitution. Integration by substitution is really a trick used to make what would be a difficult integral a lot easier just by substituting part of it for a variable. This can often be called integration by U-Substitution, most of the time because we use U as the new variable that we're substituting in. So if we just start off with a simple example, we have the integral of x plus 4 to the power of 5 dx. Here, most of the time, what you want to substitute a new variable in is something that would make the whole equation much easier. So in this case, our u would be our x plus 4, because that would simplify down just to u to the power of 5 at the moment. So then if our u is x plus 4, we then need to differentiate our u to get a du term in our integral. So if we differentiate u, this is with respect to x. So differentiating x, we get 1. Differentiating 4, we get 0. And all that is times dx as a differentiating with respect to x. Then we sub that back in to what our integrand was. So that would be u to the power of 5. Our dx is just du. And now you can see that is a much simpler term to integrate than this. So using our knowledge from yesterday's video, which was a covering of the basic parts of integration, if you haven't watched it yet, go back and watch it. It just explains how to use the power rule, which is what we'll be using now, and also some basic integration of trig, exponentials, fractions, all that kind of stuff. So when we're using the power rule, that becomes u to the power 6 over 6 plus c. Now we're not finished there quite yet. We still have to include our constant because there's no limits on our integrand, and there could, just to be on the safe side, this is explained in yesterday's video. Again, if you haven't watched it, go back, give it a like, it'll really help you. Yes, so now we have to substitute our u back in and then we'll be finished with this integral. Remembering that our u is x plus 4, so we have x plus 4 to the power 6 all over 6 plus c. And that is our integral of x plus 4 to the power 5. So now if we move on to a trickier example, this is only slightly trickier because there are two almost functions in our integral. They're times each other. Now you could use the other method of integration, or another method of integration, when doing two functions times each other. But with this particular example, it would get quite difficult. That other method is the integration by parts. But since we're raising our bracket to the power 12, that could get quite messy. So here substitution is a lot easier. Also, another way to pick up that substitution is a lot easier. It's when you can differentiate one term to get another term in the integrand. So here, if we differentiate our x to the power 4, we get 4x cubed, which is this term here. So if you spot that, then you know that this will normally be quite an easy substitution integral. So here we'll let our u equal x to the power 4 plus 17. I'll just bracket that off. Again, we have to differentiate now. So our du, so we have 4x cubed, differentiate 17, you get 0, and then dx. Now, what you might notice straight away, oh, I forgot my dx there, is our 4x cubed dx is these two terms here. So if we just block that out, this is just du. And then that's how we can make the integral a lot easier by picking a suitable substitution, which can differentiate to get rid of any other terms in the integral. So then our overall integral becomes u to the power 12 du. Because we could these are just times and we just move over there and we get du. Now this, again, we learned how to integrate this yesterday, in yesterday's video using the power rule. So u to the 13 over 13 plus c. Again, not quite finished there yet. We just need to substitute what was our u back into our equation. So overall becomes x to the power 4 plus 17 all over 13 and raised to the power of 13 plus our constant of integration c. Okay, now we're going to do some examples involving some trig functions. Quite a nice example to start this off with is the integral of sine 2x plus 6 dx. Nearly forgot it again. Not a good day for me. So we now let our u substitution 2x plus 6. Again, using our technique, we just differentiate that. We get 2 dx. Now here you can't substitute that straight in to our integral because we don't have a 2 dx in our integral. There are two ways to solve this. We can either times our whole integral by 2, or we can just rearrange to get dx on its own, which is a much easier one. So du over 2 is dx. Now we can just substitute that straight in with our new u variable. Simplifies the equation much nicer. And if you notice, since we're timesing the whole thing by a half, we can just take the half outside as a constant. Du. Again, using what we learned in the basic integration video, our integration quadrant, and remember when we are integrating we go anti-clockwise, so using that we have a half integral of sine u is minus cos u plus c. Here we could times the c by a half, but then we are just timesing a constant by another constant, so it would still be a constant. So I could write it as a half b and then let a half b equal c, because it's just constants. So we could just keep it as c just to keep it easier to write. Now that way we have minus 1 over 2 cos, if we substitute our u back in here, 2x plus 6 plus c, and then that is our integral using substitution. Okay guys, our next example is using substitution to evaluate integrals with fractions in them. For example, if you had the integral of 1 over 1 minus 4x dx. Here, this does look quite difficult to integrate. If I had to integrate it right using substitution, it would take me a lot longer. But using the substitution method, we will let u equal the denominator this time, with 1 minus 4x. Differentiating that, we have minus 4 dx. And that minus 4 just comes from, if we differentiate x, we get 1, so minus 4 times 1 is minus 4, and then times the whole thing by dx as we're differentiating with respect to x. Now, again, we're going to have to do some rearranging to that equation, just so that we can get our dx on its own, so it appears as it does in our integrand. This is very simple. We can just do minus du over 4 is dx. So rewriting our integrand, I'm just going to take the quarter minus a quarter out straight away. So you have minus 1 over 4 times the integral of 1 over u du. Now, from yesterday's video, we also learned that the integral of 1 over u, or 1 over x, just to the power 1, becomes the natural log of that variable. This is just only for when you got 1 over the power, and it's not raised to any power except 1. So then that becomes minus 1 over 4, which is the natural log of the absolute value of u, plus again our constant c. Now we can just substitute our u back in, of 1 minus 4x plus c. Here, if our u was a constant, or a positive constant, we wouldn't have to have the absolute value sign. We put the absolute value sign in, just because this could be negative and it can only be positive with the natural log. Okay, finally guys, we are going to do an integration by substitution, but with limits on our integrand. So here we have 7 plus x squared dx, and this will be evaluated between the limits of x equals 3 and x equals 1. So again, we can still use our substitution to begin with, however there will be a slight difference in our method now that we have limits. So we'll let our u equal 7 plus x, such that our du will equal dx. Again, that's just by differentiating x, you get 1 times it all by dx as you're differentiating with respect to x. So rewriting this, noting here, I'm going to write x equals 3 and x equals 1, only because we're integrating with respect to these limits for the variable x, but since we've got a new variable within our integral, we're just going to write it there just to save some confusion at the moment. U squared du. Now obviously we can't integrate between these limits with respect to u, as they're for the function, they're for the function x. So we just need to find the counterparts for the function u. This is very simple. All we need to do is use this equation right here, as u and x are related to each other. So if our x equals 3, our u would equal 7 plus 3, which is 10. Again, if our x equals 1, our u equals 7 plus 1, which is 8. So now we can just rewrite our integrand as we have up here. 10, 8 u squared du. Now we know how to integrate this u squared. We can just use the power rule that we used in the last video. So we'd have u cubed over 3 between the limits 10 and 8. Now here we don't need a constant of integration. That is because we are integrating between limits. And when we integrate between limits, the constant is not necessary, as we're only integrating between a certain interval. So the way you do this when you have limits is you take the value of the upper limit into your equation and you subtract the value of the lower limit. For example, I'll take a third out because we're dividing by 1 over 3, or sorry, we're timesing by 1 over 3 for both limits when they go in. So we'd have 10 cubed, then we're minusing our lower value or lower limit, and that is a third of 1,000 minus 512, I think. Yep. 864 and 64 times 8 is 512. Then that'll be a third times 488. Now 488 can't be divided directly by 3 because that's a fraction, so it's just easy to leave that as the answer as 488 over 3. So guys, that is just some quick examples on some integration by using the U-substitution. There are a lot more examples out there using like surds, roots, fractions, a lot harder ones with many different elements of trig. Arctan, sectan. Sectan, that's not a thing. Secant. If you have any questions, please drop me a comment and please like and subscribe if this video helped you at all. And if you haven't checked out our previous video yet and you found any of this a bit confusing, go check out our previous basic integration video and hopefully that should clip any issues you have with this video. Thanks for watching.